Hello friends. So today we are going to solve the question from rotational motion, and this question is from 2020. Only one question we are going to solve, and this is from the advanced part. So question states, a football of radius r is kept on the hole of radius small r, where small r is less than capital R, made of a plank kept horizontally. One end of the plank is now lifted so that it gets tilted, making an angle theta from the horizontal as shown in the figure. The maximum value of theta so that the football does not start rolling down the plank satisfy the figure is schematic and not drawn to scale. Basic figure is given to us. So we have a plank and which is having a small slot over which this ball is resting, and the length of this slot is given as 2r, and we have to find out the theta maximum value so that the ball does not start rolling. So here okay, so we have to keep in mind that it should not be rolling, or we can simpler term we can say that all the forces as well as torque acting on this ball or sphere should be in balance. Okay, so we have to remember that, and the forces that will be acting on it will be the gravity and the normal force because of the connection point of contact rather. Okay, so these two forces will be acting on it. So we can say that equilibrium condition and can say that sphere means stationary. It is sphere or ball or football. Let me call this a ball. Ball remains stationary if forces and torque acting on it balances. And the forces first force will be gravity, and which acts downward, on the ball's center of mass, with force, and that force will be equal to over mg. Okay. And the second force will be normal force, and that normal force will be the ball's contact at the edge. Contact at the edge. And so let us consider this in xz plane. Wherever x is along the Planck's tilt direction, Planck's tilt direction, and our z is vertical when our theta is 0. Here the normals, that is because of the point of contact, will try to roll it because of the net torque they are going to generate. Okay, and a component of a gravity will try to overcome these normals, which will or we can say that the normal forces will be balanced by the restoring forces, and the restoring forces will be because of our mg. This is the simplest form we can just explain it. So let us find out the first of all geometrical configuration. So we can say that when our Planck is horizontal, with hole centered at the origin. Centered at the origin. And we can also say that the sphere center is at the height h above the Planck along z-axis. Above the Planck along z-axis. So we can just simplest draw it. So we have this is a Planck which is now horizontal, and this is the sphere, and we say that the center of this hole, let us suppose, is somewhere here. This is acting at the origin, and the center of the sphere is at the height h, and we call this axis our x-axis and this is our z-axis. Remember, this x-axis is along the direction of the tilt. Okay, as it is going to rise, the x-axis is going to rotate, and similarly our z-axis is going to rotate. Okay. And the total, the diameter of the hole is given as 2r, so the radius of the hole is r. So we can say our hole's radius is our r. And so the sphere touches the edge of the hole at the point on the circle of radius r. Okay, let me draw it more. And this total is given as 2r. So the radius of this hole will be r. So one point of the sphere which is going to touch is also going to have a r, and other point is also going to have a coordinate as r. Okay, other coordinate we can define later on also. So it means that sphere touches the edge. Let us call this edge as A and B. Edge A and B of the hole on the circle of radius r. So this is nothing but a small circle, something like this. And we said if this is the center of the sphere, then this sphere is a height of h. So in this this is basically its you can say untilted state or initial state. Therefore we can say that in untilted state, or we can call this as initial, the sphere center let us call this as O, sphere center O. We can write its coordinate as 0, 0, h. Okay. And second, yeah, okay. And we can also say the distance from sphere center to the point of contact. Okay, point of contact on the hole's edge. And point of contact is nothing but our A, B, and that will be equal to the sphere's radius. Which is given as capital R. So we can use distance formula, which basically means that this distance will be our R. Okay. And other side also, for the B side also same. So we can say distance formula, this will be giving us r minus 0 plus 0 minus 0 plus 0 minus h whole square root will be equal to capital R. Therefore, we can say that our R square plus h square will be equal to capital R square, giving us that our h will be equal to R square minus small r square and its square root. So it means the sphere center is at the z coordinate is our r square minus small r square above the plank when horizontal, above the plank when horizontal. Now we come to the tilting of the plank. Tilting of the plank. So the plank is tilted, that is by angle theta, and so tilted the plank about angle by angle theta. So now mg is going to have two components, because now it will be something like this, and this is a sphere, and mg will be acting vertically downward. So we are going to have two components. This will have theta, so we are going to have mg cos of theta, and this will be mg sine of theta. But we have to remember the height of the center from the plank of this ball is going to remain same, that is h. It is not going to change, okay, if it is not rotating or not shifting from the hole. So we can say that sphere center remains above the hole but gravity has two components. And those will be our now it will be something like this. So this will be x-axis and this will be z-axis, okay, because we have assumed that x-axis is with respect to the plank. So if plank is moving, our x-axis is going to follow that particular thing. Therefore we can say our mg sine of theta, that will be along positive x-axis, and we have our mg cos of theta, that will be perpendicular to Planck. Now let's find out the contact point and forces. Contact point and forces. So like I said, that contact point we have called them as A and B. So if A is our in the untilted condition we call them as A and B. So the coordinate of A will be our minus r 0, 0, and B will be our r 0, 0. So we can say that our contact points are at r0, 0 and minus r0, 0. And after tilting, we have to analyze the sphere's equilibrium position. Okay, and we have our, this is our B and this is our A. Okay, so we can say, one second, let me change it. Let me call this as A and this is our B, and here also. This is A and this is B. Okay, now let us consider point A. So, and these center points are for untilted. And under untilted condition, we also know that the sphere center is at 0, 0 and our h is our r square minus small r square. So let's find out the vector form of point A. So we can say vector form center to point of contact A. Let us call this as our RA vector, and that will be r0, 0 minus 0, 0 square root of r square minus small r square, and we get this as our RA will be equal to r comma minus r square minus small r square. And we know that the distance will be equal to our r square plus r square minus r square square root. Yeah, one second. This is a square root and this is whole square. So this cancel out r square and r square goes away, and this comes as our r. And the unit vector from center to A, let us call this as n unit vector, will be equal to our r comma 0 minus square root of r square minus r square divided by magnitude, that is our r. Similarly for point B also, similarly for B, we can say our n unit vector B will be equal to minus r 0 minus square root of r square minus small r square and divided by r. And in this case, we have to remember that these are the two normals. Okay, let me draw it here. This is center O, and this normal will be towards the center O. So this is our A, so this is our n unit A, and this is B, and this is our n unit B, and corresponding normal is our NB, and here it is our NA. We can say that our normal forces NA and NB act along an A unit vector and an B unit vector towards the center. That is a O. Now equilibrium along with rolling condition. Equilibrium and rolling condition. Okay. And we do not want it to roll, so we can say the net torque about the axis through the point of contact must be equal to 0, or we can say forces must balance to prevent translational motion, because they are going to have two motions, translational as well as rotational. Rotational will be because of the torque, and translational will be because of the forces. So we can say that for sphere not to roll, net torque about the axis through the point of contact through the contact point must be 0. And the forces must balance to prevent translational. So let us consider torque about point A. And so there are three forces. One will be mg, normal at A and normal at B. You can say forces are gravity, which is our mg, downward, and mg downward at the center, which is given as 0, 0, and this is our r square minus r square. And we are going to have normal force A, which is our NA, and along minus n unit vector A. And the third force is our normal force B, which is our NB, and it will be along our n unit vector B. Okay. So we already know the two components of our mg, that is mg sine theta as well as our mg cos of theta. Okay. So you can say that our mg, two components in x direction, which is our mg sine of theta, and in z direction, which is our mg cos of theta. Okay. And in this case, because as soon as the balls try to rotate, it will lose the contact from point B, or we can say the normal B NB is equal to 0. That is a critical condition, okay, which we ideally don't want. So we can say the sphere rolls when the torque about A causes rotation. And from here we can say the critical condition is when NB is equal to 0 and sphere pivots about A. So let us make analysis of our torque. And so in this case, we are going to consider angle phi, that is between the vertical axis Z and the line from A to the center. Okay. So in this case, we are going to consider angle between z-axis and the line from A to the center. Let us call this as a phi. So our z-axis is something like this, and our point of contact is like this. Okay. And our center is suppose somewhere here. This is the line joining. Okay. And so we know that this is our radius r, and this height is our h, which we found over r square minus small r square. Therefore, if this angle is of phi, we can write that cos of phi will be equal to r square minus small r square square root divided by capital R, which gives us 1 minus r square upon r square and its square root. And this is our r. So from here we can say our sine of phi will be equal to small r upon capital R. And as the sphere is going to try to rotate, our mg sine theta will, the component of the gravity along the plank, that is our mg sine theta, will try to produce the torque about A. And for critical angle theta, this particular component is going to align that the sphere is about to rotate. So let me put it through. You can say that sphere rolls when the component of gravity along the plank causes center of mass to produce torque about A. Or in terms of critical angle, we can say the critical angle theta occurs when the projection of gravity aligns such that the sphere is about to rotate. That sphere is about to rotate. Okay, so under this condition we can say that angle theta of the plank and phi will be same. Therefore we can say that our theta max will be equal to phi, and therefore we can say our sine of theta max will be equal to sine of phi, and this is r upon capital R. So the maximum value of theta is our option number A is correct. Option A is correct. So this completes the question. Thank you.